Hello students, can you hear me? हेलो
Yes, sir.
ऑनलाइन में आवाज आ रही है?
Yes, sir.
ओके तो स्टूडेंट्स प्रवेगा टॉक सीरीज में आज हमारे साथ मिस्टर निशांत कुमार पाठक हैं। तो वो क्वांटम कम्युनिकेशन के डोमेन में काम करते हैं और आईआईटी दिल्ली में से उन्होंने अपना पीएचडी किया हुआ है। तो ये टॉक सीरीज हम लोग रखते हैं ताकि आपको थोड़ा सा प्रिपरेशन के टाइम में भी या प्रिपरेशन के बाद भी अदर फील्ड्स का भी एक्सपोजर आपको हो। फिजिक्स में कौन कौन से फील्ड हैं, उसमें क्या क्या चल रहा है। सो वी ऑलवेज इनवाइट डिफरेंट पीपल फ्रॉम डिफरेंट बैकग्राउंड and we talk about the sciences. So today Mr. Nishant Pathak will be discussing about quantum communication. So Nishant, please.
Thank you, sir. Thank you, everyone.
Just come this way.
So I am currently doing a PhD from IIT Delhi, Department of Physics, and I think I've been there since 2018, and I have done my MSc from IIT Delhi itself in physics. And I have been a long time part of this Pravegaa team since my coaching here, and I have got very great guidance from these people. So today let's give you some overview of what quantum communication is, and let's see what are the scopes if you find it interesting. So quantum communication in a nutshell, I will talk very short. I have tried to make it as simple as possible. So since the ages we started communicating with each other, we wanted that our communication be private, right? No other non-intended party would be able to listen it. So, and there always be a possibility of an eavesdropper. So when two parties are communicating, there will be always a possibility of third party who wants to listen to your private personal messages. And now in the era of internet communication, we share a lot of information like personal messages, credit card information, governments share their secrets over the internet, and defense secrets. This on the internet, how do you make this communication secure? So there are various established methods which are currently being used when you communicate over internet. So the primary requirement to communicate securely is you have some message, which can be image, video, whatever. We technically call it a plain text. So, and you need a key which must be available with both parties, the sender and the receiver. That key should be identical. So if you want to send a plain text message to someone, you make it encrypted using your secret key and then send through the internet. Since this is not in a readable form, no one in the between can unlock or decrypt it because they do not have the secret key. And then on the receiver end, since they have that secret key, they can again decrypt and read the message. Now the problem is you are sending your message through the internet. How do you send the secret key itself, right? One option is to make consider your trusted friend, give him the key and tell him to go to your friend's place and he will deliver the key there, right? But that is a cumbersome process. And let me tell you, this is actually being done in defense. This is the way they do it. So if they want to communicate from Delhi to Jammu and Kashmir, they use a trusted courier service to send this key. But you see how long it would take and how cumbersome this is. So, and on internet, we are talking to our friends. It's not always possible. So the other way is to use a asymmetric type of encryption over the top of this. So use asymmetric. So this is a recipient which wants to receive a message from you. He will generate a pair of keys. So one will be called a public key and one is the private key. public key is open to all, can be seen by everybody. So whoever wants to send message to me, they will use my public key, encrypt the message, and I can decrypt it only with my private key. And private key is only private with me. So this is the way. So when this is done in both directions, you can establish a tunnel in which you can then share the key and then encrypt your message with this AES keys. So the question is this asymmetric, which is RSA is one example, is this really future proof? Is this really secure? So we know now that quantum computers are coming, and if you have the idea, quantum computers will be having very large computational power compared to today's even supercomputers. So a calculation, so RSA is based on a kind of algorithm which is easy to solve in one direction but difficult to solve in the other direction. For example, if you take very large prime numbers, you multiply them. So multiplying is easy, but factoring is very difficult. So current your any encryption is based on this RSA, and RSA with supercomputers will take hundreds of years to decrypt your data. So we consider it safe for now, but quantum computers are coming, and these are the companies being are working, and huge amount of money is being invested in these directions. So quantum computers will be soon a reality, and if not, if it takes even let's say 10 years or 20 years, you can capture the data now and decrypt when quantum computers are there, right? That is called collect now and decrypt later, right? So we need something, a solution for this, which is not based on algorithm and which is future proof. So the answer is quantum cryptography, which I've been working on. So quantum cryptography utilizes the fundamentals of quantum mechanics. These are no cloning theorem and principle of superposition. I hope you have heard about superposition principle. I'm not sure about cloning theorem. So no cloning theorem says that you can, if you have been given an arbitrary quantum state, you cannot make a copy of it. And superposition principle, you all know, it can be in superposition of eigenstates. So if you measure an unknown quantum state, it will collapse to an eigenstate. So these are the known methods which can be used to encrypt your data. So you see the RSA, Diffie-Hellman is another type of algorithm-based cryptography. These all are non-secure in future. There are other, apart from quantum cryptography, there is called PQC, post-quantum cryptography, which is again based on algorithm, but these are special algorithm which is claimed that even quantum computers won't hack. But who knows? It is still based on algorithm. So the only theoretical security is given by QKD at the bottom, quantum key distribution. So this is proven secure, and this uses to all the principles of quantum mechanics only. So in quantum key distributions, usually you have two kind of channels, one through which you send the quantum states, and one through which you communicate the extra information you need to establish the key. So let's say you take particles of light, which are photons. So you send from one end to other end. You encode information in the property of the photon, which can be polarization, phase, frequency, time, anything. And you communicate other details through the classical channel. It is assumed that classical channel anyone can hack, but quantum channel, since they are based on quantum principle, no one can eavesdrop. So this QKD can be done in various ways. So you can use a fiber. So large number of telecom fiber is being used for internet communication. You can use free space for long distance quantum communication, and you can encode in terms of single photon states. You can use weak coherent states. So weak coherent states are basically take the classical laser and attenuate it to very sufficient level. Entangled states, you can entangle two single photons particles and then use them for this same quantum communication. There are other ways to use entangled photons like teleportation and all. So this is one of the protocol which allows to do quantum communication. So it is BB84 is one example. B92 is simplified version of BB84. So what you do?
So yes.
Two questions.
Please just ask at the end. So let the presentation finish, that you can ask. Okay.
So in BB84, you use polarization property of photons to encode information. So you use two bases. One is standard basis, other is Hadamard basis. And the polarization, so this is standard basis. You can have 0 bit or 1 bit. This is Hadamard basis, horizontal or diagonal or anti-diagonal. So this is can also have 0 and 1 bit. So Alice, so one party, the sender, would randomly prepare the photon in all these, and Bob will receive. So I will explain next. So Alice prepares these bits in a random fashion and sends the photons to Bob, and Bob receives, again choosing a random basis, and whatever basis he selected, they communicate over the classical channel and then finally establish the key. So here is an example. So let's say A wants to send this data. Okay, A's basis is randomly selected and only Alice knows. So and these are the angles for that. B will again randomly select, which can be probabilistically same or different. So you see here the bases are different, here the same. So Bob will also randomly select and arrive at some detection. Now they will compare their bases whether they were same. Okay, they can reveal this information, they will not be losing the secrecy. So whenever they have the same basis, they will put a yes, that they will accept that bit, and so they will put a yes and then use that for the key. So this 00, wherever you see a yes, will contribute to the key. Now they use part of that collected bits to check if there was an eavesdropping, right? If someone is trying to disturb the photons in between, these measurements would be disturbed and you will see an error there. So this yes is used for that comparison. So for comparison, you reveal those bits. So we do not use them again. So whichever is not used, that they become the final key. So here 010 is the final key, and this will be both. And initially the key was to be sent was this, but final is this. So before arriving at the final key, the benefit, the very amazing thing about QKD is, what is the final key? No one knows in beforehand, even Alice or Bob, right? So our works have been in news recently. So we have demonstrated 100 kilometers of quantum key distribution between Prayagraj and Vindhyachal, which were in the news. And recently we published and we enhanced the performance to 380 kilometer, and we published it in scientific reports, which was also covered in the news. So this was the field demonstration. It was between Prayagraj and Vindhyachal, and the range was 100 kilometers. This is Cuber, which shows how much error was there. So it was around 9%, but we tried to improve that, and I think that slide is missing. So we tried to improve that, went to 380 kilometer, and Cuber very less than 2%. So I was talking about entanglement. So you can use entanglement to do all kind of stuff. So this is one example. So this is based on spontaneous down conversion process. So you take a photon interacts with the crystal at certain specific condition, and that photon can down convert into a pair of photon. So this will always be in pair, and this pair will have correlations. So you see one photon will come out in this red circle, another will be in blue circle. And if you align everything correctly, you can make a cross section here. So at the cross section there, you can generate entanglement if you control all the other parameters. So with an entanglement, you can generate this kind of states which you study in your books. So quantum technologies are the most practical applications of what you study in your literature, right, in your books. So benefits of entanglement. So you see that in quantum communication, you have to send one photon to, let's say, 100 kilometer. So entanglement, you have a pair of photon, and you can send each photon to the both direction. So you can increase your span to double of the previous. So, and it increases the security and all. There are other features also. So in the whole world, these are the maps where different countries are trying to demonstrate QKD network in real life scenarios. They have established quantum communication test beds to test these kind of technologies. And after 2022, we are also on the map. So I think the technical part is over. Now I will let you know some websites which can be useful for you for your personal use. So this is a website which I run called Quantuse. So you can read various articles, let's say from quantum money, black holes, on everything, if you are keen in physics kind of things. And you can also, if you are interested in writing things, you can also click on join us and send us a mail, and you can write your own post here if that passes our quality check. And so there are many posts being updated. So in future, possibly after your masters or during PhD, if you want to do internship and all everything, you might be looking for some kind of permanent or temporary jobs. So research kind of, because we are from core research fields. So you can go to researchjobs.in. This is also run by me. So you can just go to login register and click here on the register, and you can make an account here. Just put your details, and then after verifying your email, you can create a profile, add your profile picture and all. So thank you. You can reach me in these details.
So I think after the presentation, are we able to provide the PDF to the students?
I will edit something and then I can.
Yes. Okay. So
provide, yeah.
just for the details.
Yeah, sure.
So a big round of applause. So it was a wonderful presentation, and few students, I think I wanted to ask doubt, but I wanted that at the end. तो अभी पूछ सकते हैं भाई, जिन लोगों को डाउट पूछना है या कोई क्वेश्चन पूछना है, तो he will go back to the slide and answer. I think Nishant was asking. Please ask.
Yes, sir. In the case of Alice and Bob, so they to check whatever their key is, then that is like that. So I do not understand like how can you do that.
Okay, so I said that using the principles of quantum mechanics, you disturb an unknown state, you cannot copy. So let's I can not go in very detail here, but I will try.
Yeah.
Okay, so suppose Alice sends in, let's say, this cross basis, DA basis, and Bob also receives in DA basis. But eavesdropper in between do not know. So initially, Bob also do not know what basis Alice is sending. So Eve will try to measure in a random basis again. And if he measures in the same basis, it will be fine. But if he measures in plus basis, it will create error. So if the eavesdropper measures in the plus basis, it will either get 0 or 1. Okay. Now, if he gets 1 or 0, he will try to resend it, because eavesdropper doesn't want them to know that someone is eavesdropping. Otherwise, what's the purpose, right? So if he randomly chooses the basis, it will create an additional error in the system. So while comparing this at the end, they will compare a part of the shifted key or the measured key, and then if they see a error greater than the threshold, they will discard this process and they will repeat the process once again, right? So eavesdropping can be done, but successful eavesdropping cannot be done. So you can obviously measure a photon in between, but the legal parties will definitely know, right? So it depends on the key rate. So for example, what we have done, it goes to kilobits or something. So you need very short keys, not every time. So your data can be in megabytes, but you do not definitely need a very large size of key.
Basis and reading it. Is it a long process or we can run it very easily?
It can be real time. It can be real time. Like what you need on the source, you need lasers. You can have pulse laser, which can be giving out photons continuously. You have random basis selectors. which can electronically be controlled. And on the receiver end, you have detectors, single photon detectors, which gives you the timestamps in the precision of picoseconds. So it can be done real time.
Any other question?
You also said that we can use codec of quantum communication. So can you explain this thing in little more detail?
Just repeat, Nishant, once again.
So my question is, we can use codecs of laser light to do quantum communication work. So can you explain like how can we use codecs?
Okay, so I guess I did not mention coherence as a method to do quantum communication. There are other ways like continuous wave quantum communication. I work on discrete variables. There is continuous variable where coherence is important. But I said that encoding states can be done in these. So single photons, weak coherent states, and entangled states. So weak coherent states are basically your laser only. The other name is only weak coherent states. So laser is a coherent source, right? And if you attenuate it, it becomes a weak coherent state. That's it. So see, weak coherent states are easy to make because you just need to attenuate it. You need some kind of attenuator in between, an opaque, a trans-opaque object, which can bring, let's say 1 milliwatt light to single photon level. That's it.
Okay, so I think it was a wonderful session. और बाकी अगर आगे भी कोई क्वेश्चन है तो ईमेल आईडी निशांत की दी हुई थी, तो आप उसके थ्रू भी कम्युनिकेट कर सकते हैं. ओके, सो थैंक यू निशांत, थैंक यू वेरी मच.